Hi, welcome back. Okay, now we shall go through some examples, starting with example 1-13. This is a little bit of unique question because it includes water level rising, but do not worry, the concept is still the same. So mass of flow in, okay, will always be the summation of the mass flow rate going out. So this is based on the law of conservation of mass. Alright, so continuity equation. So if we look at this case, right, it says that it has a tank of 1 meter by 0.5 meter breadth. Okay, so this is the base of the container, and then it's supposed to have a certain height, right? And water is coming in and going out. Okay, so let's say water is going. Okay, so this is water is going out at 250 liters per second. Immediately you can convert it to meter cube per second, which will be 0.25 meter cube per second. Just divide by 1000. Okay, so this is Q out. Okay, so what is exactly is Q in? Okay, the thing is that within 30 seconds, the water level increases by 2 meters. You can actually treat this, right, as a form of outflow. Okay, so what it means is that whatever comes in through the inlet, right, will be going out through two channels. The first channel is that 250 liters per second. The second channel going out is the rising of the water level. So we can say M in is equals to M dot out plus maybe M dot rising. Okay, this is another form of outlet. So you go to Q in equals to Q out plus Q rising. Okay, and since this is water that we are talking about, and water is incompressible, and so we can assume that the densities at each point are the same, so they can cancel out. So this is a main problem of volume flow rate. Alright, so Q in we do not know, but we know Q out is already 0.25 meter cube per second. So how do you calculate Q rising? Q rising is the volume of the water level that has risen over the time that it took. Okay, so 0.25 plus. What is the volume? 2 meters has 2 meter rise in water level over 30 seconds. And you have that base area of 1 meter by 0.5 meter, right? So it is actually 0.5 times 1 times 2. Okay, so this is, so it basically means this volume that has risen. Okay, across so this is 2 meter. So it has risen, so this much volume is considered the outlet. So half times 1 times 2 is the volume over 30 seconds. Okay, so your answer should be 0.5 times 2 divided by 30 plus that 0.25 that's going out. So the total volume flow rate is 0.283 meter cube per second. Okay? Right, so this is example 1-13. The next example 1-14. Okay, water flows with a velocity through a pipe of 50 mm. Okay. So so this is what happens. So you have a diameter of 50 mm. Okay, and the flow the velocity is 1.5 meter per second. Okay. And there's another pipe, 100 mm diameter, installed series at the exit of this 50 mm pipe, which means that it is connected to a bigger pipe. Okay, from one pipe to the other pipe. This time this diameter is 100 mm. Okay, so what is this flow? So first we calculate the volume flow rate in the first pipe. Okay, the volume flow rate in the first pipe, let's just say is Q1, is, according to the formula, velocity times cross-sectional area. Okay, velocity you have, and cross-sectional area is pi d square over 4. D is 50 mm, which is 0.05 meters square over 4. Okay, 0.05 square times pi divided by 4 times 1.5. 2.945 meter, times 10 to the power minus 3 meter cube per second. But you're supposed to express in liters of water, which basically 2.945 liters per second. Okay? So conservation of mass. So this is also water, right? So incompressible. So Q1 equals to Q2, where this is the larger pipe Q2, this is the smaller pipe Q1. So 2, okay, let's just use the SI unit, 2.945 times 10 to the power minus 3 will be U2 times pi d square. D is 100 mm, which is 0.1 square over 4. Okay, so this is the cross-sectional area. So U2 is just this divided by this. Okay, divide by pi divided by 0.1 square times 4. Okay, 0.375 meters per second. So how do you check whether your answer is correct or not? It's roughly there. You see the smaller pipe will have a higher velocity compared to the bigger pipe. Okay, so once the diameter increases, the volume flow rate remaining the same, it means that the speed will have to slow down. So this is what basically happens in a nozzle. No, sorry, it's not in a nozzle, it's in a diffuser. So the diffuser goes from a small opening to a large opening. So once this happens, because of the conservation of mass, your speed slows down. So U2 will be smaller than U1. Okay, where this is 1, this is 2. And this is what exactly is happening here. Smaller pipe to larger pipe. Okay, so last example. This is about splitting into 2 pipes, right? So we have 2 diameters, 30 and 20 mm, and the large inlet is 50 mm, which is not written here, but you can write it here. 50 mm. So the volume of this large pipe is 6 liters per second, and the flow velocity here is 2.5 meters per second. Okay, so first calculate the velocity here. Because I have Q, 6 liters per second, divided by 1000, I get 0.006 meter cube per second. Okay, this equals to U times A. Okay, U I don't know, but A I can find. Pi diameter is 50, so it's 0.05. Pi d square over 4. Okay, equals to 0.006. So my U will be 3.056 meters per second. Okay, so this value is coming in here. And second, the volume flow rate in the 20 mm pipe in meter cube. The volume flow rate here. So you have Q over here. You need to find Q over here. Q1. Q1 is just U1 times A1. U1 is 2.5. And cross-sectional area of this pipe will be pi D is 30 mm. 0.03 square over 4. Okay, you get 1.767 times 10 to the power minus 3 meter cube per second. So this is what's going through 1. So pipe 2. So Q is Q1 plus Q2 according to the continuity equation. 0.006 is equals to Q1, which is this, 0.001767 plus Q2. So Q2 is simply 0.00423 meter cube per second. Alright. So we have covered all the examples in chapter 1, and I hope I've given a clear explanation. If not, just feel free to approach me anytime. Thank you.